This video is presented by me, Alfarook Saleh, and my partner, Daniil Grubich, and is about our assignment 1. This project is about building and modeling a robot in a virtual test environment to program the robot to execute commands based on the functions we wanted to achieve. To accomplish this, we first had to build and mount the robot in the most optimal position on the clipboard for maximum reach. We decided to mount it on the long side of the clipboard because the robot cannot reach the end of the clipboard if placed along the shorter side. Furthermore, a section of the clipboard is unreachable and is useful for putting electronics that we don't want the robot to affect. Here you can see the two-dimensional workspace of the robot in green, or all the space the robot can reach. This is based on the physical minimum and maximum joint limits of the motors described below. Next, we need to define the coordinate frames with which to base our transformations from. In the left photo, we drew all the coordinate frames of the robot, the clipboard, and the end effector, and their respective orientations. On the right, you can see where we place the clipboard and end effector coordinate frames. Note that the end effector coordinate frame is really from the tip of the marker and not from the tip of the cap. After defining the coordinate frames, we can physically measure the DH parameters of the robot so we can simulate the robot in our test environment in MATLAB. Below is a great visual on how we found these DH parameters. Note that for revolute joints, the theta parameter is variable, and for prismatic joints, the link offset is variable. Finally, after modeling the robot, there will be some error in the modeled end effector location compared to the real end effector location. Now we use optimization to get the model to most closely match the physical robot. The left side of the table represents what variables were used to get the points on the right side of the table. Before optimization, we had an average error of around 15 millimeters. And after optimization, we had an average error of around 7 millimeters. The graph above shows the total error during the optimization process, and it's easy to see a decline in total error after hundreds of iterations of optimization. Now my partner Daniil will explain the graphical user interface we designed for this project.
Here's a quick demonstration of our GUI. Robot can be input in two different ways. One way is to individually configure the joints and using joint DH parameters panel, input the DH parameters of individual joints, as well as putting the robot X and Y coordinates. To make it easier, you can also upload the file with the pre-measured robot. Once you open it, the DH parameters are showing in the configuration shown table. And then once you click Create Robot, the tab switches to this panel where you can set the joint angle for the robot. Also, it shows the position of end effector with respect to the coordinate frame of clipboard. When joints here, forward kinematic is being performed, taking joint variables and getting a transformation matrix for the end effector. Here, another feature is moving the robot end effector by selected step. Right here, the transformation matrix is obtained for end effector, changed based on the click performed by the user, and then inverse kinematics is performed to get the joint angles and parameters for the robot, and then it being plotted. Also, you can change the view. It's the identical robot. With robot configured, now it's possible to optimize it using the optimization process. Right here, when you click optimize, it asks whether to optimize base position. For this example, I'm going to say no, because it works better without optimizing the base. The first thing it asks to open is the select optimization file with the physical measurements of the points. So here, optimization measurements. I'll open it, and then right after it asks to open the mask file, which tells the optimization function which parameters which DH parameters to optimize. Right here, it shows the red light with the text saying in progress to show that the optimization is being performed. Right here is green light with done, saying that the optimization is done. Right now, once it's done, you have to create a new robot with like the new DH parameters. Once you click it, you have a new robot that is optimized to the measurements.